We generated very reliable models of our structure that we tested. So now we want to use these models also in combination maybe with other simulation models or in a kind of a forced response analysis way, or we want to make use of the model inside or outside test lab. And that's why we came up with this state space modeling concept and the export to MATLAB or the export to NeveMu. And one of the first cases we encountered to make use of this functionality, well, it's a bit a busy slide, but in essence, what this project was about was it was an existing car, so a vehicle body that was already on the market, but a damper company wanted to add another damper to an improved version of their initial damper to the shock absorber to existing car. And so they were kind of making physical models of their damper or their shock absorber using AmaSim, so SimCenter AmaSim, trying to optimize the behavior of the shock absorber. But they also wanted to know how the damper would work in combination with the vehicle. And the vehicle, they could do measurements, or they asked us to do measurements, but they didn't have any simulation model of that car because it was not there. They didn't build the car; it was from a car manufacturer, obviously. And they also wanted to use the most reliable model, which is essentially a measured model. So they did measurements on a car body using the attachment points of the physical damper as excitation points, and then looking at some typical target locations in the car. So there was accelerometers put on the seat. There were also accelerometers at the damper points, and there was also some sound pressure measurements done at the right ear and the left ear driver, because these are also important targets. So these transfer functions, the idea is now to combine these transfer functions with inputs from a modified damper model. The transfer function as such were not directly used, but a model was derived from them using modal analysis. So we did Polymax, we did MLMM, and then we generated a state space model so that people could do time domain simulations even and even listen to the results of the new damper. So by synthesizing the sound pressure levels based on the new damper and the body model, you could really hear what was going on. It will be illustrated also with a demo of these concepts. What is the idea here? The idea is to take a model, as I was explaining before. So we have mode shapes, natural frequencies, damping ratios. And we want to put that in a model that also can be used in other environments. And then a state space model is very well suited. It's a kind of an input-output model. So the U that you see here is the excitation of the model, the input, and the Y is the output, so the response of the model. There is also kind of an internal variable, the X, and that's the state. And typically, yeah, that's an internal variable. We don't know exactly what it is, but it's needed to run the model. There exist two variants of the model, a continuous time model and a discrete time model. Here you see, for instance, the derivative of the state variable. The discrete time model is a bit simpler because these are just recursive formulas, and this is a bit more logical for measurements. There you also have a certain sampling frequency, so your data is sampled, so you have the samples of your input, and you can easily calculate your output of the model. It's just a recursive formulas. Here you would need some time integration methods, so that's a bit more complex to solve. Discrete time models are a bit easier. And so the challenge here was to make a data-driven model that people could use as a component in an integrated simulation environment. Maybe like in my example, the shock absorber existed as a physical model, but I wanted to couple that to a data-driven model of the car itself that you could do with a state space model. So what we do, we take an existing mode set and we convert it to a state space model, and you can share it in your organization in a standardized format. And the export that we offer is either MATLAB or as an FMU, following the FMI standard. I will also explain a bit what that is about, functional mockup unit or functional mockup interface. What are the benefits of this solution is that we will generate reliable models that are closely representing our measurement data, thanks to the stabilization diagram interpretation, MLMM. So we have industry-proven solvers. In the software, you can also check the quality of your state space model before exporting it and passing it on to a colleague, perhaps. So you're quite sure about the quality of your model. Maybe a little bit of theory, because at first, these two models look quite different. So you have your model, you have your state space model. How can we put our model into this ABCD model? Because these are the parameters, matrices A, B, C, D. However, if you take a closer look, we can already see much more similarities. So when you take this theoretical model ABCD, We can do an eigenvalue decomposition of the matrix A. That's standard mathematics. We have eigenvalues, we have eigenshapes, an eigenvector matrix. We then do a coordinate transformation by taking this eigenvector matrix. And then we have kind of a different model, but with exactly the same input-output behavior. So the input is still U, the output is still Y. Only the internal matrices changed. They're not A, B, C, D anymore, but lambda phi minus 1 times B, C times phi, and D. If we now take this form and we apply the Laplace transformation to that, to this analytical model, we get a representation in frequency domain. We now get a kind of a transfer function where we have all these matrices of the model. And now we are already very close to what we get in TestLab after model analysis. But rather than taking this summation, we can write this equation down in the matrix format. So you have a diagonal matrix of all your poles. You just put your mode shapes next to each other. You do the same for your participation factor. And we end up with this equation. If you compare now both forms, you see that large part of the job is already done. It's like this C times phi matrix, that's just our mode shapes. The phi minus 1 times B matrix, that's our participation factors. Our poles are identical here. We just have here a bit of troublesome terms, the lower and the upper residuals, and they are quite important to include. They do not easily transfer into a state space model. So the trick that we will apply there, and you will also see it in the demo, is that we are going to substitute these lower and upper residuals by some artificial modes that are far away from our frequencies of interest. And then we can include them in this general part of this equation. And then we can do the mapping on a state space model. That's a bit the idea. Here you see a bit the illustration of this state space modeling concept and the replacement of the lower and upper residual by some what we call residual compensation modes. So let me go through this graph. So the red curve is a measured FRF, as you can see. The green one is what we would do in a traditional way with modal analysis. So we have good representation of the data inside the frequency band, but we also need to include some lower residual behavior and some upper residual behavior to really model the dynamics of the modes outside the band within the band of interest. So outside the band, of course, we didn't look at this data. We only looked at the effect of the modes inside the band. And so we need to include a residual, and the same for the lower frequencies. Otherwise, we would not get nice fit. With the state space model, we cannot just take the green synthesized FRFs. We need to change a bit the lower and upper residual formulation. And you see here a mode appearing, a kind of a highly damped mode at lower frequency. There is also a mode at higher frequencies. But overall, the blue curve and the green are closely matching each other, especially in the frequency band of interest. If you would just ignore this lower and upper residual, because it's a bit difficult to model maybe, you would end up with the pink situation. And so you see that the peaks are maybe there, but you see that overall you don't fit the data very well in your frequency band of interest. So you really need these out-of-band compensation modes to get a realistic representation of the data in your band. So that's why we paid quite some attention to these. What are the applications? So once you have a model, you can use it in time domain and frequency domain for simulations, for control studies. You can do forced response analysis, so you can apply an input to your state space model and calculate the output. It's used in structural coupling. That was a bit a damper case I showed before. Substructuring, virtual sensing is a potential use of the method. And why did we select state space models? Because they're kind of a reduced order model. We only have a few parameters, A, B, C, D, and we represent a whole set of FRF data, basically. As I said, you can use it both in time and frequency domain. You have also two flavors. You have a continuous time model and a discrete time model. And it's also possible to change even the quantity. So you can go from displacement to velocity to acceleration based on some theoretical derivations. In the software, I will do first the generation of a state space model. I will export it to an FMU, and then I will load the FMU in TestLab and do some simulations, some time domain simulations to illustrate what we can do with these models. So if you're interested to know more about this FMU, so it's not a Siemens invention, it's a standard that people use to exchange models. And if you take a look at this website, oh yeah, here it is. So here you see a list of companies that are supporting these FMU standards. So everybody is there basically that is generating models. And these FMUs allow to change models and use models in a different environment. So there's like 170 plus tools that are supporting it. So this is a website maintained by a committee behind FMU. Okay, so now it's time for a demo. I will open a different test lab project. Okay, let's maybe take the right data. So this was, the geometry is not really appealing. It was just a tube, and it was not really a modal test. It was an environmental test, vibration control test, where we had a shaker exciting a tube with some sine sweep excitation. But it's a nice example to illustrate what we can do with a state space model. So there is like 10 accelerometers and 1 output. It's also not a force measurement, it's a voltage that we send to the shaker. That's typical for environmental testing. So it's a G per volt transfer function. We are more used to G per Newton, but that doesn't really matter. It still has modes, it has dynamics, so we can still do modal analysis here. Here you see the complex MIF of the data, all the peaks from 20 to 2000 Hertz. We go to the stabilization diagram. We find a lot of stable poles, so let's select them. Sometimes you have to be a bit careful. You can also, if you observe that the automatic selection was maybe not perfect, like here, for instance, when you zoom in, you would see that you have 2 modes. So I can select a second one here, because it's clearly there. Now I can calculate the mode shapes. And then we can have a look already at the synthesis results. You see that it's maybe not great. So you see the green curve is not really on top of the red one. Maybe for some others it's a bit better. But yeah, this is not yet a good quality model, I would say. So let's really go to MLMM and use 100 iterations to really improve it a lot. You can always stop the iteration if you think you reached convergence. So now we are at around 30 iterations, 34. And yeah, maybe it's not changing too much anymore. So we can stop it. And we can look at the improved synthesis now. And now we see a very nice fit of the data. So the green curve is almost perfectly on top of the red one. Yeah, maybe not for all FRFs, but at least for the most important ones. We get a very nice representation of the data. So now let's generate a state space model. That's also an add-in. I already activated it, but you have state space model conversion. When you activate the add-in, you have this state space model checkbox that you can switch on. And it's immediately calculating the state space model. So that's the blue curve you see appearing now. And it's almost perfectly on top of the green one. Here you see the parameters that influence the model. So maybe if I take the defaults, that's the default model. So you see blue and green are maybe not perfectly on top of each other. So it's possible to play with the parameters. And especially here, this situation can improve by taking a bit of lower damping for this compensation mode. So it's really possible to play with it. So we have a continuous time model and a discrete time model, as I explained before. For the discrete time model, we need to select a sampling frequency. And the default here is 50,000 Hertz. So it's way above the frequency range of interest. And that's also needed. We go to 2000 Hertz, but we put an upper residual mode at 5 times higher, so at 10,000 Hertz. And then it's also recommended to sample the model again 5 times higher. Let's check if we take a lower one, 25,600, whether we are still having a good model. That seems to be the case, so the blue curve did not change too much. We get a warning though that we are a bit low. But it's interesting to see the effect of sampling. So if you're really exaggerating and taking the sampling frequency here in the frequency range of interest, so if I take, for instance, maybe 1200 Hertz, you will see that we get a very bad model. And you even see the aliasing around 1200 hertz. So that's the model is mirrored around that frequency, and it's completely not representative for the data. So that's why we have this functionality here to really generate a discrete time model rather than generate a continuous time model, pass it to a colleague that need to discretize it. But without knowing the frequency content of your data, it's a bit tricky. So that's why the conversion can be done also here in TestLab, so that you're absolutely sure that you get a very high quality model. So if you again take 25,600, I'm representing very closely my data, and I will have a good model. So I can store it as a FMU of MATLAB, as I said before. So let's maybe do as an FMU. Yeah, that is already on the preparation, my FMU. Okay. I will close now TestLab model analysis, and I will go to the process designer to illustrate the use of an FMU. So it's not model analysis. Neo channel processing, process designer. I will open the same database, but now in process designer, TestLab Neo. So I made this process with the FMU loaded here, but I can maybe illustrate what's happening. If I take a new block, FMU, it's an empty block, but here I can import an FMU. And if I now take the FMU that I just generated, demo, I can open it. And here we can inspect the model. So there is inputs to the model. And you see here we have the TestLab names appearing here. We have to map it. Maybe on you can change the name here, put a different DOF ID here. And it will be important because we will excite the model, and the DOF ID need to correspond to the DOF ID of your input. You also see your outputs here, where you have all the TestLab DOF IDs, and the units are also there. Okay, so I did it here. I already did the mapping, so I changed this name into time series, a DOF ID corresponding to a time series I have in my database to be able to excite my model. So I can delete this one. What is also important is that we excite the model with data that has the same sampling rate as the model. And in TestLab, I showed model analysis that we use the sampling rate of 25,600. So we need to make sure our excitation is at the same frequency. So that's why I have this resampling block. Then I go back to the original sampling rate, 6,400, and I will calculate the spectrum. So the spectrum that comes out of my model and the spectrum that is directly coming from the data. Let me load this into input basket. SVSW1. And now I need only to load the relevant time data that corresponded to my model in. I will not use the strains. Voila. Input basket. So now I loaded like an input, so a drive in voltage. That's the one we can see here. So it's a voltage that is driving my model. So it's exciting my model. It's a sine sweep in voltage. And we will calculate the outputs. At the same time, I will split off the other channels here, which are the responses, the measured responses, as you can see here illustrated. And I will also calculate the spectra from these. And I can then compare the spectra from the responses measured with the responses coming out of my model. That's a bit the idea here, to illustrate that we are quite close to the data with this model. So now let's run the FMU. Everything should be in the input basket. So I push run. I forgot to give it a name, but that's fine. I think it will take 10-15 seconds or so to run. The data can be seen here. So we now have like every time 2 time series. So if I take a different view and I click here, you see, for instance, the simulated data from the model compared to the measured data. So you see the time domain, they are quite closely matching with each other, all these channels. So the model that we put here in between is able to generate time data that really is almost the same as on the real structure. In frequency domain, though, you would see some differences. So maybe this one is So at lower frequencies, you see a very good match between the data and the model. At higher frequencies, you start to see some deviations. One of the reasons is that the model was generated using low-level random data, and now I'm trying to simulate a high-level science sweep with this model. But you see that this FMU is really able to take a model, and you can use it as it was, like a real structure. So you can excite it, you can drive it with this voltage here. So that really the time domain excitation we use to excite our model. So you see a science sweep excitation here, and the model will calculate. We will calculate the responses of that model here in Desktop Process Designer. Okay, so if I go now for the final slides. So again, this example I explained, we also run that, and that's a bit what you see here. So we have a very good model of the data. We put it in a state space form, and now if we take the damper loads, the shock absorber loads, the forces, we can excite our model with these dampers, and we can calculate, for instance, here the sound pressure inside the cavity of the car by using this model, a state space model. Here I illustrated the state space modeling concept, so you can generate a state space from modal analysis. You can package it as a MATLAB model or as an FMU and use it in your preferred simulation environment.